So, hello again students, and welcome to this module about district heating, district cooling and electricity production. This is the second technical module, and we will discuss briefly the preparation of the heat carrier. What you will learn in this module is a little bit about the temperature levels, the heat carrier, and the demand set on the heat carrier from different aspects. You will also learn a little about heat pumps. Now, as a preparation, I want you to read the first part of chapter 2, pages 12 through 19 in the IRENA Roadmap report. On page 19, you will find a headline saying Heating and Cooling Energy Mix, and I suggest you stop reading there, because that is what I will bring up in the next module. So, pause the recording now and read those pages. So, welcome back again. You might well argue that I am biased, and I am, but I want to especially emphasize what was said on pages 14 and 15 in the text you just read. There are so many advantages gained by central production of space heating. And what we will concentrate on right now is the flexibility, which is in turn the basis for energy supply security, as mentioned on page 15. So the basis for the flexibility is at first that the temperatures in district heating systems are very low. You're never ever above 200 degrees Celsius. And that means that most any primary source of energy can be used. Because of that, you can always make use of locally produced waste or biomass as a source in the energy supply. There will typically, in a mature system that is, be several production units. So one input point can be located so as to use, for example, surplus heat from a paper mill located in the industrial estate outside the city. And another one, beside the dump, uses municipal waste as its fuel. And the third one might be, say, a solar heating plant. Let me give you a concrete example. Go to the home page of the International District Energy Association and then search for the case study from Paris. I selected that one only because it's easy to find, but feel free to browse around for any other studies. In case you downloaded the Paris case study, then look at page 5 and read about the energy mix and look at the map to see how the production units are spread relative to the network. The next thing is then the environmental gains obtainable. The environmental benefits with a district heating system will of course be a strong function of the system it replaces. In case the individual houses were all heated by solar heating systems and the district heating system is supplied from a boiler house, then is there an environmental step backwards, no matter which fuel is used in a boiler. The combustion process in itself will always produce airborne pollutants. But in most cases will the individual houses have their individual boilers. Even a gas-fired boiler will produce airborne pollutants. This is inevitable. If a number of small boilers are replaced with a sufficiently big unit, then can the total amount of emissions be significantly reduced because of the better control and the installation of proper cleaning of the exhaust gas. Let's then have a look at how the heat can be generated. And we start by determining approximately the temperature span we will be working in. The starting point must be set by the end user. The end user will want to use the hot water delivered in a heat exchanger to produce hot tap water and to produce comfort heating. As for tap water, do many, if not most, countries have a legislation stating how the monitoring of Legionella bacteria shall be done. In some countries has this been specified as a lower temperature limit. For the second thing, hot water for the internal heating system, there will be no sanitary aspects, since this water is intended never to escape from the system. But then there is a huge difference from old wall-mounted radiators that may demand 80 degrees to heat the house, and a modern floor heating system where some 30 degrees is sufficient. So the customer farthest away must be supplied with district heating water that meet these demands. And that holds for 365 days per year, 24 hours per day. To guarantee that, will the production unit have to pump out district heating water that is significantly warmer? And in northern Scandinavia, would the output temperatures from district heating plants be some 120, even up to 130 degrees during winter? But then the high temperature increases the heat losses, so you always want to pump out water at the lowest possible temperature. The limit is set by what arrives at the last customer. So during summers the output temperatures are significantly lower. As the water goes around the grid, will each individual customer extract heat from it. Through the history of district heating has there been a successive development. In old systems were the customers often connected according to the single tube concept. The principle is shown to the left. The yellow arrow is the main supply pipe. The upper part of the supply pipe to the dashed line is called the forward pipe, and the part below the dashed line is the return pipe. So the customers extracted the hot water to their heat exchangers from the main pipe, and after the water had passed through the heat exchanger, it was returned to the same pipe again. If the customers are connected this way, you will realize that the volume flow of water in the main pipe more or less remains constant along it, but the temperature in the main supply pipe will drop. So the last customer would get water that was of a low temperature. Today, other customers normally connected according to the two-tube principle. That name is a bit confusing, because there is in principle only one pipe which makes a U-turn. But anyway, the customers are then hooked up between the forward and the return. So what happens now is that the volume flow in the forward pipe successively decreases, but the temperature remains more or less constant. Now that's not true, of course, because of losses, but the temperature remains high. So doing it this way, will the last customer still have hot supply water? Now, no matter how the customers are connected, by the far end does the water come back to the heating plant again, and then it has a low temperature, and then it is again reheated and pumped out again. The return temperature should be as low as possible, but no value can be given for this, because it depends on so many different factors. So just as a general indication of the temperature levels, this is about what we are talking about. So let's say that what you want to do in the production plant is basically to heat up the return water from, say, 30 degrees and then pump it out again at some, let's say, 130 degrees. The very most extreme case is that you have free access to oxygen-free and non-corrosive water at, say, 130 degrees temperature from a natural source. Examples of that can be found in Iceland. In that case, you may not even have to bother about a return pipe. Or maybe the thermal situation is similar, but the water is corrosive or there is too much oxygen. Then you will have to treat the water first and then just go on. Or you can install a heat exchanger. Maybe you have access to geothermal energy, but at too low a temperature. In that case, you can use a heat pump to transfer the energy to the circulating water. If industrial waste heat is available at a temperature level above 130 degrees, you can use a heat exchanger. To arrive at temperatures like 130 degrees using solar heaters, they would have to be either reflecting or vacuum tubes, but then it's no problem. So there are several different options, but in most cases the main alternative is to use some type of fuel-fired boiler. And then you would have to choose an environmentally friendly fuel, and you would have to have advanced flue gas cleaning. The heat carrier in the main supply pipe is water, and for that water are the most important things: first, that the water has the correct pH value; second, that the oxygen content is low; and third, that the water is free from particles. The main aim is to avoid deposits in the pipe and to avoid corrosion that might lead to fractures. Most common is to reduce the amount of salts, again to be safe from corrosion. And then there is often a need of softening, which means that the amount of dissolved calcium and magnesium should be reduced. So, deoxygenation, ion exchange units and demineralization will be needed, and then a pH adjustment. And there must also be a similar cleaning system online, so that eventual makeup water meets the same quality demand in the case of leakage. Now, I assume you have no real problem understanding the fundamental idea about using hot water straight from the ground. And I assume you have no problem with using hot water from an industry. And I assume there are no problems to understand how solar heaters work. And I assume that you know how a hot water boiler works. But I know that sometimes there are problems to understand the idea of a heat pump. I'm not going into any details of heat pumps in this lesson, but you have to understand how heat pumps work. If you do not, then I would suggest you first take this video lesson on heat engines and basic thermodynamics. The video is almost 1 hour and 20 minutes. But if you do not have the basic thermodynamics, you will not understand what I'm going to tell you later. So if you feel the least bit shaky about thermodynamics, then take that lesson now. The video I refer to now is only less than 12 minutes and will show you the relation between the heat engine and the heat pump. So look at that video now. Now you are well aware of the theoretical relationships between the heat fluxes and the temperatures, and you know the definition of the coefficient of performance. The refrigerator you have at home is most likely a compressor type refrigerator, and that is also what you would like to use in a geothermal district heating system. So this then ends the presentation in this module.